we're looking at errors in representing numbers in binary. So I'm going to start with an example of the number system that we use day to day. So a problem with base 10. Now, if we try and represent the fraction 1 over 3, a third, using base 10, then we end up with this. Okay, so in real life, you can represent a third by cutting, let's say, a cake into 3 equal parts. That's absolutely fine. The problem comes about when you try and represent that as numbers in base 10. Now we end up with this infinitely recurring 0.333. Now, we can shorten it to this, fine, but it is a problem. And the reason that it's a problem is that we can look at the factors of the base number. So the factors of base 10 are 1, 2, 5, and 10. Now, 1 and 10 is a given. For whatever, if you're using base 64, then 1 and 64 will be factors of that base. So we kind of ignore that and we just refer to the prime factors. So the non-1 and the non-base number itself. So the prime factors of base 10 are 2 and 5. And because this denominator is not a prime factor of 10, then we're going to end up with these representation errors. So since the denominator is 3, which is not a 2 or a 5 or a product of 2s and 5s, we can't represent it exactly. So this is as close as we can get. Now, there's another example of this, which is 1 over 7. Again, the denominator is not a prime factor of base 10. It's not a 2 or a 5. So we're going to end up with a representation error. Okay, so in both cases, we have something called a representation error. And that purely comes about because of the base we're using. Now, if we were to use base 12 to represent 1 over 3, it would work out perfectly fine. In fact, there's the representation. No repeating decimal places. So just a reminder, in base 12, that would be the units column before the decimal point, and then the first fractional part would be 1 over 12. And if we actually do the math there, that comes out as a third. So 0.4 in base 12 is an exact representation of 1 over 3 of a third. So in this case, we would say that this base number has no representation errors when it comes to this particular fraction. Now, base 2 has a more amplified problem because the only prime factor in base 2 is 2. And so that limits us hugely when we're trying to represent certain numbers, certain fractional numbers. Now, this will mean that the denominator is always a 2. So if you look along the bottom here, this represents our binary representation of these decimal numbers. They're all powers of 2. So with that in mind, what are the kind of representation errors that we bump into? So 0.1 in binary, in x over 2n, we can't represent it exactly. The same with 0.2. Any of the ones that are coloured in here, we can represent those exactly. So 0.25, 0.5, 0.75, we can represent those no problem. Everything else, we will have these representation errors. That's not an issue in base 10 because all of these numbers we can represent perfectly, exactly, using these fractions. So base 2 brings its own representation errors because of the limiting factor that its only prime factor is 2. So representation errors in base 2. What do we actually mean by this? So if we were to take the value 0.2, so 0.01, sorry, 0011, and that's repeating, so 0, 0, 1. If we look at this, we can't ever get to 0.2. So it's only those representations where it happens to fall on the decimal number that we are looking for, or we add together to make the decimal number that we're looking for, that we can represent those exactly. Okay, so if we actually look at the values that come out, if you look at these targets that we can't actually represent, we can get close to them, but we can never hit them exactly, given the fact that we're using base 2. So, truncation. Now, truncation can exist because, for example, here I've set the number of bits to 1, 2, 3, 4, 5, 6, 7, 8. Because these inaccurate representations result in repeating patterns, we have to decide at some point where we're going to cut that repeating pattern off, where we're going to say we can only use a set number of bits. So computers and computer memory have strict storage limits. Certain mathematical operations result in binary numbers that we just can't fit into those storage limits. Sometimes it's hardware related, sometimes it's software related. So sometimes the software that you are using when you do a division, for example, you might end up with this recursion happening and it just can't store, it can't handle those numbers, the length of those numbers. So here are some reasons why you would have to start chopping or rounding off binary numbers. So floating point numbers, for example, it's impossible to store those fractions or to represent pi given a number of bits. So you could go on forever, you could have an infinite number of bits representing these decimal numbers, but you have to chop them off at some point. Casting, so between data types, if you turn a floating point into an integer, well, integers don't store the decimal part of the number, so you have to get rid of that. Okay, so you would truncate it or cut it off the end. Division operations, if you divide two integer numbers together and it results in infinitely repeating products, then you can't represent that. You have to, at some point, chop off the repetition. So let's actually look at this. We'll start with truncation, and in both cases for truncation and rounding, we're using the value 0.1. So here's a binary representation using 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 bits. So this is the representation of 0.1. Now, if we placed a limit on this where we could only use 8 bits to represent this number, then we'd have to chop off the least significant 2 bits from the original number. That would leave us with this, and that's purely truncation. Now, the effect that truncation has is that if this was what the original value was representing, by truncating it, we're kind of rounding down. We're getting further away from the value that we're trying to repeat. But that's a limitation that's placed on this representation, given the number of bits that we can use. Now, the same number, if we try and round it, is slightly better than truncation. So if we have that original representation, and this time we're going to cut it in the same place, but there's a rule that we have to stick to, which is the notion that if the first bit of the bits that we are discarding, that we're chopping off, if that's a 1, we've got to add 1 to the remaining value. So I'll show this in action. So we've truncated it, now we add 1. The reason that we add 1 is because the first bit of what we're removing was a 1. You don't do this if it's a 0. So we're going to add 1 on, and there's the representation using rounding. Now, the original representation, before we rounded it, and this would be the same for truncation, was this. By rounding it, we're actually getting slightly closer to the representation we're looking for. So in terms of how far away from 0.1 this rounded value in the original is, and the truncated value, well, that's slightly further away from 0.1 than this. So this is closer to the intended value. So that's why rounding is slightly better than truncation. As always, thank you for watching.